So today the one big concept that we want to figure out is how to take a real life situation and translate that into a component form of a vector. Okay? So we have what are called direction angles. All right? And when we are looking at a particular situation in real life, we rarely have the components. Okay? However, if we're able to convert a real life situation into components, that makes things a lot easier, okay? Because then we can do vector addition, we can find magnitudes, we can do all kinds of different things with those components that are much harder to do with the vectors themselves, okay? So as we know, vectors have a magnitude and a direction. Now, by definition, the direction angle for a vector is going to be the angle in standard position. Okay? So you'll notice over here in this diagram that we started with, okay, here we have an angle that's in standard position. Okay? Why don't you just sit here so you can. Okay, so we start at the positive x-axis and we rotate clockwise or counterclockwise. All right, rotate up. Now, in this particular instance, what we have is this airplane that's flying at a velocity of 100 miles per hour at an angle, a direction angle of 210 degrees. So it's going downwards. Okay, we're looking at this from a side view, not from a satellite view. So we're watching this plane go down for a landing or something like that. Okay, so what we're going to do is we're going to actually convert this vector 100 miles per hour, 210 degrees into component form. Okay, now you can see I have this formula here where I have vector v is going to be the magnitude of vector v times cosine of the angle times the vertical component, or sorry, horizontal unit vector, and then also times the sine of the angle times the vertical unit vector, okay? And I actually have a typo here. This should not be a plus sign. This should be a comma separating the two components, okay? Because what we're getting here is a vector, all right? We're getting a vector. Now, you could also write this as the magnitude of v, and using this vector notation, just do cosine times the angle instead of the ij. Oh wait, no, I'm sorry. This had ij in it. Why is that deleting? That was correct. I'm sorry. The ij, you have a plus sign. We could have also done it like this. Cosine x, sine x in the brackets. Okay? So I'm sorry. That wasn't a typo. That was correct. And that's probably the form that you will use more often, is with that comma instead of the ij notation. But we should be familiar with all of it. And you guys know that when you multiply a vector by a constant, that magnitude, you simply multiply the two components by that magnitude. All right, so looking at this scenario here, the magnitude of our vector in this case is what? This airplane, what's the magnitude? How fast are we going? 100, okay? 100. So 100 miles per hour is our magnitude of the velocity. It's our speed, okay? Remember, magnitude of velocity is speed. And then the angle is 30 degrees below the horizontal. Now this you kind of have to translate, all right? In order to get the proper direction, you have to translate 30 degrees below the horizontal as shown. Now if we weren't given a picture, they would have said it's going 30 degrees south of due west, okay? Here's west and here's, well, this wouldn't be south because it's up and down, all right? So below due west, or below the horizontal, going west. But regardless, however you look at that, our direction angle in standard position is going to be this 210 degrees. So,
How would it not be on the other side?
well, that's just the picture they gave us.
Oh.
It could have been. It's just that's the picture they gave us. So using that formula that we had above, the magnitude of vector v times the cosine of the angle, we could use theta, we could use x, times the sine of the angle. We're going to then say, okay, well this vector v is going to be 100 times the cosine of 120 degrees times the sine, or not 120, a little dyslexia there, okay, 210 times the sine of 210 degrees. All right, and this, guys, I wouldn't be surprised if you had something that was maybe not this exact problem, but similar to this on IB exam or whatnot, where you're not allowed to use the calculator. How do we know the sine and cosine of 210? Because we remember our unit circle, okay? All right, that's not going to go away. We got to make sure we know our unit circle. All right, so just as a reminder, on our unit circle, this is a 30-degree reference angle. At 30 degrees, if you recall, at 30 degrees, we had the point on the unit circle that was root 3 over 2, 1/2. And remember, on the unit circle, all the points are cosine of the angle, sine of the angle. Okay? So, and by the way, notice that's why we do cosine of the angle, sine of the angle to make our vector. All right? So, cosine of 210, we're in the third quadrant here, and if you recall how we figure out the sines of our trig functions, all students take calculus. So tangent is positive in the third quadrant, which means sine and cosine are both negative. All right?
How do you know it's positive?
Huh?
How do you know it's positive?
That's just how it works out.
So which one's
If you work through the trig. Okay, we could talk about unit circle more to get that. But right now I just want to make sure we're getting this vector idea. So the cosine of 210 is going to be a negative root 3 over 2. Negative root 3 over 2. And the sine of 210, sine is also negative in the third quadrant. So that's a negative 1/2. Okay? And then we're multiplying this by 100. So, if I actually do the multiplication, I've got a negative, root 3 is about 1.71 something, okay? So times 100 is going to be 171 point something over 2. And then negative 1/2 times 100 is a negative 50. Alright, so this is a negative 85.5, negative 50. Okay? Now, the question is, okay, that's nice. What does that mean? Okay? What does this component vector mean? Because if you don't understand it, it's not going to be useful. Alright? So, this as our horizontal component means our plane is moving to the left, or we could say west in this case, at 85.5 miles per hour. All right? So if we ignore the fact that it's going downwards, just looking at it going from right to left or east to west, it's going to be going 85.5 miles an hour that direction. The minus 50, on the other hand, tells us that it is getting closer to the ground, or it's approaching the ground at a rate of 50 miles an hour. Okay? So in other words, if the plane were to land at this angle, you'd slam into the ground. That would be a pretty rough landing because it would be hitting the ground at a speed of 50 miles an hour. Okay? That's why jumbo jets, I believe the angle's something like 18 degrees of their descent. Or maybe 18 is, I knew it at one point. I think 18 is actually fighter jets landing on an aircraft carrier. They land at 18%, or 18 degrees. And that's a hard enough landing for them. I think jumbo jets or something use more like 10 degrees, if I remember right. But anyways, the whole reason is because they want to, the lower the angle, the smaller this vertical component will be. Because they got to keep going fast enough to stay in the air, but they got to go slow enough vertically so that it's a nice smooth landing. Okay? So, we're approaching the ground at this rate at 50 miles per hour. We definitely don't want to land at this angle. Okay? But that's what those components are giving us. At an angle, we're going 100 miles per hour. But horizontally, we're moving 85.5. Vertically, we're going 50 miles an hour. Okay? That's why this is useful, because then, if we know that we're at a certain height, we can figure out how many minutes it's going to take us to reach the ground. Okay? And if we know how many minutes it's going to take us to reach the ground, and we know how far the airport is away, then we can use the horizontal component to figure out, okay, are we going to make it to the airport, or are we going to land too early or too late? We can make adjustments. All right? So, but again, that's how we would convert to the component form. Here's another example using a little bit of physics, and it actually uses a little bit of geometry as well. Okay? Here we have a force of 600 pounds. Now, when you weigh something, that's the force of, it's measuring the force of gravity on an object, right? If you studied weight before. Which direction does gravity push? Down. Straight down, okay? So, in this diagram here, that force of 600 pounds is required to pull the boat and trailer up a ramp. So that is going to be this vector right here. Notice this vector right here is parallel to the ramp, okay? We just drew it down below here. Okay? So that is 600 pounds of force. Now I don't know what the angle, well actually I do know what the angle is. The angle is at a 15-degree angle. Okay?
Would you have to make it go from like the other one, like how we found 210?
Well, actually, because we have it like this, it already is. See? This would be like our positive x-axis, and it's rotating counterclockwise. So in this case, the angle is already given to us.
Wait, what?
In the right way. Okay? Standard position is from the positive. If we treated this as our origin, Here's our positive x-axis.
Yeah.
It's rotating up just like in standard position. Okay? All right. Now, that's our 600 pounds. We are asked to find the combined weight of the boat and the trailer. Now, like we just said, weight is a force straight down. So what we're actually being asked to find here, the combined weight of the boat and trailer, is this vector right here. Okay, can you guys see that? Not really. Let's try this color. That's a little bit better. A little bit easier to see. Okay, so that's the vector, and we're actually looking for the magnitude of that vector. Okay? Now, in this case, we actually don't have to write it in a component form because we can simply use some right triangle trig. All right? I'm going to call this vector W for weight. Okay? Vector W for weight. And what I want really in this problem is to find the magnitude of the weight. Okay? So that 600 pounds is the magnitude of the vector pulling the boat up the ramp. We want the magnitude of the weight. So all we have to do is get our 15-degree angle in the correct position. And that's where some geometry comes into play. All right? We see that the ramp is at 15 degrees up from the horizontal. Okay? It's 15 degrees up from the horizontal. That, if you look at your different angles, that means that this angle right here is going to be, that's going to be 75 degrees, right? Because we have a right triangle here. Okay, 15, 75, 90. All right? Well, if I look up here, notice there's a 90-degree angle on the right-hand side. There's 75 right there. So this little angle right in here,
90.
total would be 90. So this little piece is 15. Okay? So there's the 15 degrees. And notice, once we figure all that out, I know that's small now. Once we figure that all out, notice what I'm looking for, the weight is my hypotenuse, and not squared, that's the hypotenuse. The 600 pounds is across from the angle I have, so that's my opposite, and I know that sine,
Wait, I thought 600 pounds is the hypotenuse.
no, look, 600 is that little leg down here.
So weight's not the hypotenuse?
The weight is the hypotenuse. Okay, that's what I'm looking for.
600 pounds is not weight?
No, 600 pounds is force. Weight is just another measure of force that happens to be measured straight down to the ground. Okay? This is an amount of force that's being used to pull this boat up the ramp. Okay? They're both pounds of force. Okay? But notice here I'm using right triangle trig. The sine of 15 degrees is 600 over W. And now I can simply solve for the magnitude of W. 600 divided by the sine of 15, which that's not on our unit circle, so we can use the calculator. Okay? And real quickly here, 600 divided by sine of 15 is 2,318 pounds. Okay? That would be the weight of the boat and the trailer combined. Okay? Okay, so this last example here, guys, is kind of a good model of an IB style of problem. all right? We have formulas that we're using and things like that, and it's nice to be able to use that formula, but we also want to be able to use formulas for things that they aren't necessarily directly used for. I mean, it's not like, hey, we have an area formula, we're going to be finding area all the time. No, you might know the area and want to find out something else. Okay? Here, this problem, we have two different forces acting on an object. Okay? And we want to find an angle between the forces given the magnitude of their result. Okay? So this is kind of an interesting situation. So let's take a quick look at this here. It says, find the angle between the forces given the magnitude of the resultant. And it says, write force 1 as a vector in the direction of the positive x-axis and force 2 as a vector at an angle theta with the positive x-axis. All right, so let's actually examine what's going on here. Okay. Drawing a picture is going to be important. So I'm going to draw my x and y axis. And this first force, the 45 pounds, I'm going to make like this. Okay, so here's 45 pounds of force pushing that direction. And then at some angle, we don't know exactly what angle, so we're calling it theta because that's what we're trying. That's what we're trying to find here. We have this force here at 60 pounds. Now you might say, well, wait, that's not the angle between the vectors. It actually is, because here's the situation, all right? And this is where students kind of have trouble with vector addition and relating it to real life situations, okay? So we have this vector addition, and the resultant vector would be this right here. Okay, and that is 90 pounds. Notice I intentionally did not draw this like a right triangle. Okay, whenever you draw things, you want to avoid special cases. Also, notice I drew it so that theta was an acute angle, but I recognize it's possible it could be obtuse. So I'm not going to go just based on what it looks like here, because I just made that up. But what's challenging is to recognize what's actually happening. So we have some kind of an object here, and the forces involved would be that 45-pound force this way and the 60-pound force this way. And because of the way we drew it, that theta is going to be the angle between those two vectors. Okay?
So they don't have the same origin?
Well, that's the thing. They're both attached to this object. They're both pushing on this object somehow, or pulling on it. We're not sure, but it doesn't matter. But the angle between them is going to be that. So basically what I've done is I've shifted over that other vector so I can do vector addition. Because remember, vector addition, you always do the first vector, and then from where you end up, you draw the second vector. However, if we were observing this happening in real life, it might look something like this. Okay? Maybe one guy's pulling on a rope this way and one guy's pulling on a rope this way. And then the end result is going to be this, 90 pounds. Okay? So if you think about it, we have two people pulling on a box or something like that, two slightly different directions with that angle theta between them. The box is not going to go the way the one guy's pushing, and it's not going to go the way the other guy's pushing. It's going to go some direction kind of between them. Okay? It's kind of like if you have a pulley system, you know, and you're lifting a box with two different ropes. One rope is pulling this way and one rope is pulling this way, but the box goes straight up. It doesn't go one side or the other if you're pulling evenly, you know, it goes straight up.
Okay, so it's not gonna matter how you draw it then, right?
It's not going to matter how you draw it really, as long as you understand what's going on. And really the key drawing is this one down here,
Yeah.
that shows the vector addition.
Okay.
Okay, so here's the question, and we're going to have to go back to some pre-calculus to think through this. How are we going to figure out the angle?
So you have to do like SOHCAHTOA.
We're on the right track. We can't use SOHCAHTOA because it's not a right triangle, but we are going to use trig.
Cosine.
What?
Like,
Oh, come on, what were you going to say?
cosine.
Okay, it has to do with cosines, but it's not right triangle. We had the...
The 30s. No, actually.
I know it in Spanish.
You know it in Spanish?
Yeah. Can I translate?
Sure. Someone else doesn't figure it out before you get it translated.
I was gonna say, like, I remember in geometry we had like side.
Okay, that was like congruent triangles. Okay.
Yo también no sé Google Translate.
Trigonometry.
We are going to use trigonometric functions, and it has a cosine in it. Oop. You have
We
it?
did this in physics last year and I just don't remember it.
It's the law of cosines. Do you guys remember that?
Wasn't it cosine thing?
1 minus sine squared. Oh.
That's a Pythagorean identity, but you need to know those too. All right? It's been a while, all right? So let's look at this. We have c squared equals a squared plus b squared minus 2ab cosine of angle C. This is actually in your formula booklet. It's called the cosine rule or law of cosines. I forget which they call it in your formula booklet.
When do we know to use the...
Well, we know to use it in this case because we have all three sides and we're looking for an angle. Now, one challenge here is that we're actually looking for an angle that's an exterior angle. So we're going to use the law of cosines to find this x right here. And then how will we find theta after that? Yeah, subtract it from 180. Okay? So we're going to find cosine x. Now, the key, if you remember setting this up, it's been a while. The key is that the angle that you use and this side that's over here, C, have to be across from each other. So which side are we putting over here?
90.
The 90, okay? So 90 squared, and then the other two sides, it doesn't matter which one you call A and which one you call B. So 45 squared plus 60 squared minus 2 times 45 times 60, okay? And now we just have to do some arithmetic and stuff, some 8100, 45 squared is going to be 2025, plus 3600, plus 2 times 45 is 90, times 60 is 5400, cosine x. Alright, so we subtract the 2025, we subtract the 3600, okay, and we get 2475. Someone with the calculator should probably be checking me on these.
I feel like your math's probably better than my calculator.
No. Alright, so that's right. We divide by 5400, cosine x,
0.458.
okay, 0.4583. Just leave that in your calculator, and then what do we hit at this point? How do we find x?
Inverse cos.
Inverse cosine, okay? Make sure that, well, it doesn't say what we want to do. So you want to do this in degrees,
Yeah.
okay? Just be aware, guys, because in SL, AP Calc, it's kind of easy because they always do radians. But in SL, we kind of switch depending on the context. So just double check your mode on your calculator to make sure you're in radians when you need to be in radians and you're in degrees when you need to be in degrees. So what do we get here for X? 62.17, so 62.72, okay, so 62.7 if we do 3 sig figs.
Okay.
So that means that theta is 180 minus that 62.7. So 117.3. That's going to be the angle between them that'll give us a resultant force of 90 pounds. Okay?
Yeah.
Alright, so hopefully this kind of shows you the connection. There's a lot of connection between trig and our vector stuff that we're doing now. So this will be helpful in bringing some of those things back to memory, hopefully. Okay?